chemistry, this is the answers video to day 77, which deals with two subjects related to thermochemistry, the enthalpy of formation and bond energies. Okay, so let's go over some of these answers. What does thermochemistry study, and why is heat energy important in a chemical reaction? So we answered that in the day 75. I wrote that out. So thermochemistry studies the heat called enthalpy going into and out of a chemical reaction. And what it tells us is, since the only kind of energy entering or leaving a chemical reaction is heat, it tells us how much energy is needed to make that chemical reaction go forward, or how much is released by that chemical reaction. And it tells us the energy that's in the bonds when they break and are reformed in products. Okay, so heat energy is the only kind of energy coming in or out of a chemical reaction. All right, next, what is the definition of enthalpy of formation? Okay, so the enthalpy of formation is the delta H of the reaction to create 1 mole, that's a key, 1 mole of a compound from its elements in their most stable form. That's another key. So an example, to make CO2 you need C graphite. That's the most stable form of carbon, not diamond, not anything else. And O2, which is a gas, so not oxygen, not a single oxygen atom. The most stable form of oxygen is an O2 molecule in gas form, and that'll produce 1 mole of CO2. Okay, what does delta HF mean? It actually, the F should be subscripted like that. So delta H with the little circle F is the standard enthalpy of formation. So standard conditions are 1 atmosphere pressure and 25 degrees centigrade temperature. And the little circle means standard. So it means you're doing the enthalpy of formation at 25 degrees and 1 atmosphere. All right, why do bond energies provide only an approximation of the enthalpy of a reaction? So for example, CH bonds appear everywhere in hydrocarbons. Okay, CH4, C3H8, C2H6, they're everywhere. So a CH bond can vary depending on the strength. The energy in a CH bond can vary depending on the size and structure of the molecule. So not all CH bonds will have exactly the same energy. So the bond energy, what that implies is that the bond energy method of figuring out the energy coming in and out of a chemical reaction is only an approximation. Okay, so let's get going on these. Okay, so compute the enthalpy of a diamond going to graphite. And this shouldn't be here. That's an error. Scratch that out. What you're trying to figure out is what that delta H is, just like we did with Hess's law. Okay, so we're going to do the same thing with Hess's law. So we need the graphite. There's the target. This is the target. We need the graphite on the right. Here it's on the left. So I'm going to call this 1 and 2. Come down here. And we're going to switch it. So the CO2 is going to come over here. This is 1A. Okay, and I'm jumping ahead here. Okay, and the diamond needs to be on the left, and it is here in this reaction number 2. So we're just going to leave reaction number 2 the way it is. Okay, and let me go to my enthalpy. Since I reversed this reaction, number 1 got reversed, I'm going to change the sign on this. Okay, and number 2 did not. Nothing changed, so that delta H stays the same. Okay, now we got to verify that the reaction, these two reactions together match up with our target. So we have CO2 in 1A on the left and in 2A on the right, so they cancel. We have O2 on the right in equation 1A, and on the left in equation 2A, they cancel. So all we have left then is C diamond goes to graphite. And then the delta H then, so that's the correct reaction that we have for our target up here. So delta H is this minus this. And what that gives us is negative 1.9 kilojoules per mole. Again, this is always kilojoules per mole. So why is that significant? Energy comes out. That means the reaction takes place naturally because chemical systems want to go to lower energy. And we're going to talk about another type of energy later in the course, but for right now we're dealing just with enthalpy, delta H. So what that means is that diamond, carbon in diamond form, wants to eventually degrade, if you want to call it that, or go to a lower energy. It eventually wants to move to carbon graphite. So graphite is more stable than diamond because in going from diamond to graphite it gives up energy. Giving up energy means it becomes more stable. Alright, let's keep going. Okay, so here we have enthalpies of formation. Okay, now on the video there is, on the lecture video, which you should watch before you do this, there's a formula. So I'm going to write it here. I'm going to actually write it at the top because I need a little space down here to do this. So what it is the standard enthalpy of formation, we defined that earlier, equals N times the sum of the delta H of the products, I'll just abbreviate that prod, minus, so it's these guys go first in the equation, be careful on that, okay, minus N, number of moles, times the sum delta H of the reactants. That's these guys. So these guys go first in this equation, and these guys go after, and it's a subtraction. So let me show you how I do these. Again, you want to just develop some technique so you don't make mistakes here. Okay, so here we go. We're going to start with CO2 because it's in the product. And so CO2 is right here. Okay, so we're going to put CO2 is negative 3. Then we're going to add to that, because there's a plus sign, 2 times H2O. So H2O is right here. And I'm going to omit the units of measure because they take up space. And then I'm going to put that all in a big square bracket. Okay? So we're going to add those two. Next, we're going to subtract CH4 right here. Negative 74, so I'm going to put this. Plus, again, you're using the plus sign here, and it's O2. O2, so that's 2 times, but O2, so here's a rule, is that an element, so an element has 0, that's a 0, whoops, 0 kilojoules of enthalpy of formation. So I'm going to put a 0 there. Now we do the math. Be careful on your math. So I'm just going to pause and do that. Okay, so for the products, which are the ones that come first, it's negative 965.1. That I've done all the math on this. Now you got to watch out because this is H2O liquid. Now, if you come down to your chart, H2O liquid is negative 285. That's what you see here. But gas is negative 241. So this is one case where you really do need to pay attention to the state of matter. Okay, now over on the other side, we've got to put the negative sign in, and then negative 74.8. The 0 goes away. So be careful, this is going to become a plus sign. So it's going to be negative 965.1 plus 74.8, because the negative turns into a plus sign, and we get 890.3. Negative 890.3 kilojoules, and that's how much energy comes out when it makes sense. This is a combustion reaction. You're burning CH4 in oxygen. You light a match to it. It starts to burn, produces CO2 and H2O. And that's the amount of energy that comes out of it. Okay, that's the delta H. Okay, so again, what did we do here? We figured out the delta H of this combustion reaction using the enthalpies of formation of each of the reactants and products. Okay, we figured out the delta H of the overall reaction. All right, let's keep going. Okay, so here we have 5 enthalpy of formation problems. I'm going to do, I don't know if I'll do them all, but anyway, let's go ahead and see how they're done. And it's not that hard once you get used to them. So here's the table for enthalpies of formation. Again, you should write the formula at the top of the page so that you don't confuse it. So it's standard enthalpy of formation. And I did not define what this is. It's the Greek letter sigma. You've seen it in math class. It means the summation. So it's a summation, and then you have to multiply by the number of moles. Okay? So let's go ahead and let's just do these. So we'll find. So we're going to remember the products. These go first. So we'll go ahead and do that. It's H2O gas. It's right here. Square bracket it now with negative sign. Now we're going over to this side, and they're both 1 mole. Everything here is 1 mole. Okay, so we're good on that. All right, next is the reactants NaOH and HCl. So what I'm going to do is combine these two first, and then these two second, and then get a grand total after that. Okay, so I combine these two numbers to get negative 652.8. These are all kilojoules. Combine these two numbers to get negative 519 kilojoules. And then again, you got to watch out for your negative signs. Then I had that negative sign in. That's part of the formula, the subtraction. So this minus a negative 519 is the same. Remember, two negatives turn into a plus sign. So negative 652.8 plus 519 will give you negative 133.8. So watch out for the negative signs. They can be tricky. All right, let's keep going. Okay, so 2CO plus O2 gives you 2CO2. All right, so let's do that. Same formula. Okay, and we don't have an enthalpy of formation on this table for CO, so let me give it to you. So that's the enthalpy of formation for CO. Okay, so let's go ahead and plug that in. And O2 is a pure element, so its enthalpy of formation by definition is 0. Remember, inside the square brackets, it's a plus. You use the same plus signs that you see in the equation. Now, why do I use square brackets? Because I think double parentheses are confusing. So I want to have everything on the products in parentheses, as well as the individual numbers, because you have to multiply them by coefficients. And then same thing on this side. So I just don't like double parentheses. I think they're confusing to see. So use square brackets as the second set of parentheses. Okay, we'll go ahead and do the math on this. Okay, so negative 787 is what we got from this. Negative 220 is what we got from this. You have the double negatives there, so that becomes a plus sign. So it's negative 787 plus 220. And that would give us again, this let's be more precise here. It's kilojoules per mole. For every 6.022 times 10 to the 23rd, that's how much energy is given off because it's a negative number there. All right, keep going. Okay, so I'm going to add these up, come up with a total there, add these up, come up with the total there, and then we'll do the final subtraction. Okay, so we took the square brackets and summed those up to get negative 965. Over here it was just simply negative 74.8 because oxygen is 0. Also notice that we had to use H2O liquid, which is this one right here. Alright, so you got those two subtotals. Do the subtraction, you get minus 890.3 kilojoules per mole. So that's heat given off by combusting methane, CH4. It's going to emit heat. It's going to be warm, okay, or even hot. Okay, so that's the answer to that. Let's keep going. Okay, so you see where we got the numbers, 2H2O, and that is in liquid form, so it's the 285 number, and 2 times SO2, which we got down here, and then on the reactant side we have 2HS, 2 moles of that right there, and that's 20.1. Wherever that went, right there. Okay, and then the oxygen, pure oxygen, is going to be 0. Alright, so let's go ahead and do the math on that. Okay, so we combined these two to produce that. We combine these two to produce that. Again, it's a negative, it's a subtraction, and that's a negative, so that becomes a plus sign. So when you add negative 1163.8 plus 40.2, you get this number, and I left the negative sign off. Do that. So that is a negative 1,123 kilojoules. Means it's exothermic. Means it's going to lower energy for that reaction to take place. All right, let's do the last one here. There. And that gives us, again, most reactions are exothermic. They give off heat energy to go to a lower energy. We will learn later in the course why some are not exothermic. Some actually can take in energy, and we'll talk about that at a later time. Okay, so that takes care of enthalpies of formation. Okay, so now we're going to compute bond energies based on a chemical reaction, and this is the least accurate way to do this, but it can be done, or it's still done, and you could be asked on the AP exam about this. So what we do is we need to count how many bonds we have total. So here's a balanced equation, and you really should draw the Lewis dot structures for these when you do these, okay? Or at least be able to picture them in your head if they're simple. So what we're going to do for this is we're going to count the number of CH bonds. Okay, so we're doing CH single bonds. These are all single bonds. Okay, so how many molecules of CH4 do we have? We have 1. So I'm going to call that mole. You can call it a mole or a molecule. It's 1. And then how many bonds do we have in each molecule? And we have 1, 2, 3, 4 CH bonds. So I'm going to multiply those. And then I got to multiply that by the bond energy in a CH bond. And according to this table, it's 414. Now notice we're doing the reactants first and then the products, not like enthalpy of formation. So you want to keep that straight. So this is reactants, product. We're doing exactly the order that you see it in the chemical equation. Okay, so we got 414. Okay, and I'm going to set these up first and then do the math in a minute. Okay, and then that's it. Now we come over here and we have number of molecules of oxygen, O2. We have 2. I'm going to draw a line to be sure you don't get confused with these. Times how many bonds? You have 1 double bond, 1 O2 double bond. Okay, so you have 1 of those, 2 molecules, 1 double bond. And then what is the energy in an O2 double bond? And you find that it is right there. It's 498.7. These are all positive numbers. The subtractions and negatives will come later. Okay. All right. So I didn't give myself enough room to. That's okay. All right. So now we go to CO2, and you have one CO2. So that's how many molecules. I didn't write bond here. And this should be energy. You don't have to write these headings, but just keep straight what they are. Okay, so molecules of CO2, we have 1 times, there's 2 carbon-oxygen double bonds, times 2. Okay, and then what's the energy? Now come up here, and you have carbon-oxygen double bond, and here you have carbon-oxygen double bond. What's the difference? This one has an asterisk, and if you go down to the bottom, it says the bond energy for CO from CO. It should be CO2. It's hard to read the 2, so that's for a CO2. This is for CO2, so you can go ahead and write that here. This is for any other carbon-oxygen double bond, okay? So we're going to go with 799. Okay, I'm going to draw a line here. Okay, now, and this was bonds. There's 2 bonds in each molecule, and this is the energy. Okay, you've got 2 molecules of water, and each one has an oxygen-hydrogen single bond, an HO single bond. So there's 2 of those per molecule, and then you come up here to find that, and it's right there. It's 460. All of these are positive numbers at this point, okay? So now we go back and do the math on these. You can actually do the math as you go along. I'm just doing it, so I'll do it all at one time here. Okay, so I did the math on this. I came up with this number. This came up with this number. This came up with this number, and here. Now this is where you got to understand the concept. Energy goes in to break bonds. That's on the reactant side, okay? So I'm going to write that down here, reactants. Energy goes in. That does not make it an endothermic reaction. It becomes endothermic or exothermic based on the overall reaction, not just the one side. No matter whether it's endothermic or exothermic, energy always goes in to break the bonds. So we're going to add these 2 together and call them a positive number. Okay, so when we add the 2 reactant energies, you get this number. I recommend you put a plus sign to emphasize that it's energy in at this point. Now coming out, we're going to add these 2, but then we're going to realize that this is a subtraction because it's energy out. Okay, so I'm going to write products, and we call that negative delta H. So it's going to be a subtraction of that, okay? Rather than calling each of these negative, we're just going to add them together and call it a subtraction. So let's do that. Okay, so these 2, again, energy's coming out, so we're going to call that a negative 3438. And now we do 2653.4 minus 34.38, and that will give us negative 784. So this is when it becomes exothermic. Not here or here, but here. It's an exothermic overall. The 2 sides together is exothermic, and that's kilojoules per mole. Okay, so it's a lot of messy arithmetic to do these, so that is your final answer right there. All right, okay, let's keep going. All right, now we're going to come to this one. You already have the Lewis dot structures for that. So we have 2 types of bonds here: C, carbon-carbon, and carbon-hydrogen. So let's start with the carbon-carbon. And in this you have 2 molecules of C2H6 times the number of bonds of carbon-carbon. That's 1. You have 1 carbon-carbon single bond. And now we have to come to our sheet here. And carbon-carbon single bond is 347. Now we have to do the carbon-hydrogen. You have 2 molecules again, and you have 6 carbon-hydrogen, 1, 2, 3, 4, 5, 6. And we come up here to the chart, and it tells us carbon hydrogen is 414. Okay. Now I'm going to come over to O2. You have molecules 7 times you have one oxygen-oxygen double bond. So there's one for that. And then we come over here and we see oxygen-oxygen double bond is 498.7. Okay. All right, I'm going to draw a line here so we keep all this straight. So this is reactants over here. And now we'll come over to the products over here. Okay, so we have number of molecules here is 4. And there's 2 carbon-oxygen double bonds in each molecule. So times 2. And then the energy, so it's going to be, remember there was that special case for carbon dioxide, CO double bond for carbon dioxide is 799. Okay, and we'll do the math at the end. Okay, finally, again, I draw a line. I don't want these things to run together. Actually make this a little shorter. It's not a big deal. You'll see why. Okay, you got molecules of water. You got 6. Okay, and there are 2 oxygen-hydrogen single bonds. HO and HO is 2. And you just come up to the chart again. All very routine after you've done it a few times. And it is CO right there, single, HO, sorry. HO is right there, 460, we used that one before. Okay, and that will get us our number. So I'm going to do the math. Okay, so let me walk you through the math. For the carbon, you had 2 times 1 times 347 gave you that many kilojoules, 694. For the carbon hydrogen, again, you had 2 molecules, but you had 6 of those. 1, 2, 3, 4, 5, 6, and 414 was the number you got off the sheet. So that's the number. You add those two together. That's the total amount of bond energy in 2 C2H6 molecules. Now you come over to O2. It's an OO single bond. We got that off the paper, 498.7, and you have 7 of them. You have 7 molecules, but 1 bond per molecule. So 7 times 1 times that, and it gives you this number. Now that's energy in. Those are reactants, okay? So the reactant side, you have to put this energy in, so it's positive, and if you add those two numbers, you get 9152.9. Now we come over here, same thing, 4 times 2 times 799 gives you this number, and it's going to be energy coming out. So I put a negative sign there. Okay, when products form, energy comes out, always, no matter whether it's endo or exothermic. Same thing here, we have 6 water molecules, 2 HO bonds in each water molecule, and the energy in those is 460. So you get this, and that's energy coming out. So when you add these two numbers together, you get negative 11,912. Now the grand total, this is what determines whether it's exothermic or endothermic. This number minus this number gives you negative 2,759. So that is an exothermic reaction because overall heat comes out of it. Okay, I'll leave this last one for you to do, but if I leave one for you to do, I expect you to do it. If you leave it blank, you lose a lot of points on the assignment, okay? This is not a copying exercise, it's a thinking exercise. So do this one on your own. I'll check it in class for you, okay? Now we have a couple more problems to go. They're stoichiometry problems. So this is just like we've done stoichiometry before. And so it says how much heat is released when 4.5 grams of methane gas is burned in a constant pressure system. The enthalpy for the reaction for 1 mole of methane is negative 890 kilojoules. We figured that one out earlier. Okay, so let's write the reaction here. It's going to be 1 mole of CH4 And if you remember the balanced equation, if you don't, it's okay. It's 2O2. I'll give it to you here. And that's going to produce CO2 and O2. And you got 2O2 here. Okay, so 1 CO2 there. Okay, all right. Oh, excuse me, H2O. Apologize. And H2O. Combustion reaction always produces CO2 and H2O. Confused myself. So that's going to balance that, that's going to be a 2 there. All right, so there you go. All right, now that gives you a delta H of negative 890. Okay? So, in other words, 1 mole of CH4 produces negative 890 kilojoules of heat. But we have a different amount of CH4. We have 4.5 grams. So we need to do a molar mass conversion. Okay, so do that down here, 4.5 grams of CH4 times, and if you remember your math, it's going to be 16.5. So it's 1 mole of CH4. This is just a simple molar mass. Carbon is 12.01. Hydrogen is 1.01. You have 4 of them. So it's going to be 16.05 grams of CH4. Okay, and if you do the math on that, you get, okay, and that gives us 0.28 moles of CH4. Okay, so if 1 mole of CH4 is going to produce negative 890, then 0.28 moles of CH4 is going to produce 0.28 kilojoules. I said moles, kilojoules of 8 times 890. Let me say that again. If 1 mole CH4 produces negative 890 kilojoules of heat, then 0.28 moles of CH4 will produce 0.28 times 890 kilojoules. Okay, so we'll go ahead and say that 0.28, giving myself enough space here. Okay, so moles of CH4 cancels, and I get 0.28 times 890, and that is going to give us negative 249.5 kilojoules. Okay, so 4.5 grams of methane converts to this many moles of methane. That many moles is going to give us that many moles times that number, or negative 249.5 kilojoules. Okay, I'm going to leave the last one for you to do. Again, don't skip the ones that I leave for you to do. Those are the ones I'm really going to look at, see that you know how to do them. Okay, that takes care of this answers video.